All right, so we're doing a problem here. We have a mixture. We have a pressure cooker and a rigid metal vessel. So we can assume adiabatic of total volume, 2 liters, initially contains 1 liter of water and 1 liter of headspace containing dry room air. The initial temperature is 20 Celsius and the initial pressure is 1 bar. The lid is then put on and the cooker is heated to 120 Celsius. Calculate the internal pressure at the new state. So we have an initial temperature of 20 C and we're going to 120 C. That means our delta C is 100. We start at 1 bar and we're trying to find the final pressure of the pressure cooker. So basically, to draw it out of the situation here, we got 1 liter of water and 1 liter of dry air. First, we need to make the assumption that 1 bar is equal to 1 ATM. And then air is an ideal gas, so we're going to find the total numbers of moles of air in the initial state. So using the equation PV equals nRT, we can rearrange this to find moles. Moles is PV over RT. We plug in our values. We have a pressure of 1 atmospheres. And we have 1 liter of air. And we're going to divide that by constant in liters ATM moles K, which is 0.08206 liters ATM over mole K. And we're going to multiply that by 293 Kelvin. Plugging that all into our formula, we will find that we have 0.04 moles of air in our pressure cooker during the initial state. Now, when the water is heated up to 120 C, we have now, there is a small change in the amount of water that we have. So here we have 1 liter of water. However, this water level probably dropped a very minuscule amount, delta X. So we can just ignore that change and say that we still have 1 liter of air, because not all of this water is going to boil up at 120 C. But we do want to calculate how much water did boil up at 120 C. So to do that, we're going to use the same ideal gas equation, and we're going to find the moles of H2O in the mixture at 120 C. So number of moles is PV over RT if we plug in our values. Now we have to find the pressure at 120 C of water. And if we go to our steam tables, we can see here that at 120 C, we have a pressure of 1.985 bar, which is the same as, or very close to 1.985 atmospheres. So if we plug in 1.985 ATM, and our volume is going to stay the same at 1 liter, and the same gas constant, 0.08206 liters ATM per mole K. And we're going to multiply that by the new temperature in Kelvin, 120 plus 273, which is going to give us 393 Kelvin. You can see all our units cancel out, and we are left with 0.062 moles of H2O. Now, the total number of moles we have is simply 0.04 moles of air we found previously, plus the number of moles of H2O. And if you wonder why it's still 0.04, it's because it is a closed rigid system. So the number of moles in the beginning equals the number of moles at the end. So 0.04 moles of air plus 0.062 moles of H2O. That's going to give us 0.104 total moles. Now, using our ideal gas equation again, we need to solve for the final pressure. So if we divide everything by V, we get the pressure is nRT over V. If we plug in all our values, we have 0.104 moles, total moles, times the ideal gas constant, 0.08206 liter ATM per mole K at 393 Kelvin. And our volume, remember, in the beginning is going to remain at 1 liter. That's the tricky part about this question. You would think it's 2 liters, but remember, all of this water does not evaporate and turn into steam. And we're only trying to calculate the pressure of this air up here because water is an incompressible substance. So, and remember that this change, there is a small change, because I know intuitively that doesn't make sense. There is a small change in volume of the water, but it is very small. So for this purposes, we're just going to ignore it. So after all of these calculations, you plug this all into the calculator, you should get something around 3.36 ATM as the final pressure. And that's your answer.